All right, so here we are. Now, I forgot, I think there's 28 people in this class, so not every single one of you is here. So maybe we'll wait a couple of minutes for everybody to jump in. Yeah, a few people are still joining. It's 8 o'clock in the morning. I know it's early, very early, especially for a math class. So why don't we do this? Let's go over to Moodle and see where all of your information is stored. Let's see, where is that? There we go. Okay, so here's Moodle. This is the pre-calculus page. And you can see that I've posted the syllabus. And there's chapter one has been broken up into two halves, chapter one and two. Oh, sorry, 1A and 1B. And then down here, these are practice problem sets, which we'll be working on, not right away, of course, but as we go along, we'll be doing a lot of practicing because, of course, this is a math class, and the only way to really learn it is to practice like crazy. So we'll be going along and learning new concepts, and then every so often we'll stop and we'll do practice problems. Eventually, down the road, we'll have exams, of course, but right now we want to focus on learning the material and then getting some good practice with it so that when the time comes, we can review for the exams and be ready for them. All right. Now, this is, of course, pre-calculus. This is not calculus, it's pre-calculus. So you'll see a lot of interesting concepts in this class. If you're going to take calculus one, this is the prerequisite for that. So you'll be plenty ready for that class when you get into it. If this is your last math class, well, at least you'll learn a lot of important ideas that you can use in your other classes. And this certainly satisfies your math requirement. Oh, okay. So let me just, that's actually a good thing because that means you really won't miss anything. Okay, very nice. All right, so in the meantime, as more people are showing up, here we go. Let's take a look at the syllabus since it's open. All right, now I just realized I forgot, I messed up on the syllabus already. I can tell because I've got room numbers in here. We're not having a room number. Okay, this class is 100% online. I'll have to fix this syllabus. Sorry about that. I didn't realize I'd left this in here. The last time I taught this class was last spring when everything was more or less normal, at least when we got started. So forget these two. We're not going to have any actual physical classes. We're going to be online the entire semester. And so I'm going to replace these two with online, which is what it should say. But the rest of it looks good. TBA, the office hours, there's no actual physical office hours, of course, but if you want to arrange office hours, you can do so by sending me an email and we'll figure it out. And other than that, if you have questions, you can always send me emails. Now, I do want to mention one thing here. This is, of course, my purchase account, but the invitations that you received all came from a different account. And there's a reason for that. Let me just write this down for you on the screen. That's the account that I used to send you your invitations. Now, why did I do that? Because your names are all in an Excel spreadsheet, your names and email addresses. And in order for me to send you an invitation, of course, every one of you has to be listed in that email. And I find that with Gmail, it's easy to take a batch of email addresses and send it all out to everybody on that list. Whereas for some reason with this purchase email account, it's not possible to do that. It needs to be set up differently somehow. So for me, it's just simpler to send out your invitations directly from my account. So you can get in touch with me at either account, either my purchase account or my Gmail account. It doesn't really matter to me, but I just want to point out that you can expect to get your invitations from my account just because it's easier. It's technically easier for me to do it that way. All right, now there is a book. Now, fortunately, I'd stumbled onto a book which is actually not available as a physical book. It is only available online. In fact, let me show you what it looks like. I have a copy of it right here somewhere. Here it is. I discovered this organization called OpenStax. And what they specialize in doing is making books that are free and available online for anyone to download them and read them. And this is the book we'll be using for this class. You can see this is the pre-calculus book, of course. And I have it right here on my hard drive, obviously. I thought it was kind of cool that this book is completely free, and it's a very good book. So this is the one that we're using. So the address that you need to download it is right here in the syllabus. Right there, Pre-Calculus by Jay Abramson, OpenStax. This is the actual email address, https openstax.org. And you notice it's not spelled properly, it's Stax, S-T-A-X. So you're going to discover when you get there is that they have other books as well, which you may be interested in. Oh, here it is. Look at that. It went right there. So what they're going to do is offer you other books as well. Let's see, what else do they have? Let's say you're interested in math. Look at all those math books you could get. You could get pre-calc, you could get calc 1, 2, and 3. You've got statistics here. You've got all kinds of wonderful books, but it's not just math. They have, for example, humanities. Oh, all right. Well, not that many humanities. They have quite a few business books, including especially accounting, it looks like. And they have all kinds of nice stuff. But from our, look at all those math books. But from our perspective, the key is that they have our pre-calculus book. And so that's the one we'll be using. And that way it'll be free. Okay, you'll have access to it at all times, and it's free. Okay, which is awfully convenient, I think. And I think this is also the wave of the future. Most likely, future textbooks will all be online like this, and they'll probably have ads in them to, obviously to compensate for the loss of revenues. So that is our book. And what else do you need to know? Oh, man, I lost my place. Here we go. Now, calculators. This is the kind of class where you probably could benefit from having a calculator, but it's not absolutely necessary because, the types of techniques we'll be using are really solving equations, not so much calculating results like the average of a group of numbers or something like that. So I always recommend that you have either the scientific calculator, the Texas Instruments TI-83/84. If you have a business calculator, the best bet is the Business Analyst 2 Plus. And also, you may not be aware of it, but your cell phone has one too. If you look at your iPhone, let's see, where is this thing hiding? Hold on one second. Let me show you what I'm talking about. Right there. You see that right up there? There's that app calculator. If you hit that button, it'll show you a simple little calculator, which is not very impressive. It's very basic. But if you turn it on its side, look what happens. Whoa, it suddenly turns into a full-blown scientific calculator. I don't know if you were aware of that or not, but there it is. It's been there all that time, just waiting you to take it out and play with it. So now you know. So you can use that. You can use the Texas Instruments BA2 Plus. You can use this one or any other calculator you may have. Like I said, you won't be doing a lot with this calculator. The one thing I do want to point out, though, is that, and I don't know the details myself, but I believe that scientific calculators do have some basic calculus functions built into them. But I don't really, like I said, know all the details. So if you own one of these things, you might want to investigate that. This one, the TI-84. There it is, TI-84. If you already have one, you should at least investigate what kind of calculus functions it has. If not, I wouldn't I wouldn't spend the money to go out and buy a new one because it's about $100. But if you do already own one, you might want to look into it. Now, it turns out that there's also online, and we'll look into these as we go along. There's a couple of nice websites that can help you with these calculations as well. Okay, so we'll investigate those as we go along. They're especially useful for helping us visualize what a lot of these mathematical techniques look like. Drawing graphs is often a big challenge with pre-calculus and calculus. So luckily there are now many, many nice websites that will help us do that. Because, let's face it, these functions are very complicated, and sometimes drawing them can be a major challenge. And so from time to time, what we would like to be able to do is visually see what these things look like as we're working on them. So I'll mention those as we go along. So you might as well take advantage of the technology and let the website draw the functions for you so that you can visualize what they're looking like. So actually, while we're at it, we're talking about it, maybe I'll show you a simple example of this. Let's go find, now the first one that I've stumbled onto is this thing called Symbolab. Okay, Symbolab. I didn't mention it in the syllabus, so I guess I'll add that to it. Now, what I'd like to do is draw a simple diagram. I'm going to use the function y equals x squared. Watch how easy this is. And it's going to offer to draw a graph for me. And there it is. So if you've forgotten what y equals x squared looks like, it's a parabola that starts at 0, it faces up, and this is what it looks like. And there you go. Now, you probably could copy this, if you wanted to, onto another document. Let's see. I don't know. I haven't tried that. Copy. Oh, there you go. Copy. Let's see if I can paste it into this document. Oh my God, there it is. Now you have your own copy of y equals x squared. It's so pretty, you might be tempted to print it up and post it on your walls next to your other posters. Is anyone tempted to do that? Maybe. I mean, look at that. How cool is that? Imagine having these in your room. How impressed would people be when they come to visit you? Very impressed. Okay, so if you want to make a splash with your friends, why don't you print up some of these functions and hang them on your wall in a very obvious place? But really, no, the purpose of this is to help us visualize what these functions are that we're analyzing during the course. All right, now, what else do we need to know? Let's see, here we go. So yeah, so there are other calculators you might need, but I think any one of these will do the job. So, all right, now the topics are listed over here. And you'll notice that as we get down towards the bottom, chapter 12 is actually called Introduction to Calculus. So now, by the way, oh, I almost forgot. What I recently discovered is that this Zoom meeting setup has the ability to let us do polls. So I'm going to have one right now. I'm going to ask the following question. Here we go. And the question is, are you going to take Calculus 1? Now, this is a very easy one, yes or no. Okay, so when I post this, you'll be able to answer that question, and we're going to find out who's very ambitious in this class and wants to go ahead and take.
Thanks.
Okay. All right, so there it is. So let's see what you think about that. All right, wow. So far, it's a tie. Oh, yes is moving ahead. Oh, it's back to a tie. Uh-oh, no, yes is falling behind. Yes is ahead. And we have one more critical vote to see who wins. There we go. Look at that. A dead even tie, 50-50. You don't see that very often with these polls. Okay, so half of you are going on to take Calc 1 and half of you are not. So when we get to the end of the semester, you'll be ready to go. You'll already have seen some of the most important concepts in Calc 1. And let's see, where were we? Here we go. Yes, so that's why I chose these particular topics. I wanted to make sure they're not only learning important ideas, but that for people who are going on, that you're really well prepared for what's coming in Calc 1. And a lot of these topics I think you'll find very interesting. Some of them, in fact, many of them in the early chapters, you've likely seen before. Maybe it's been a while. So in my other math classes, I also like to do this other survey where I ask the following question. Let's see, let's try this one. How long has it been since your last math class? All right, so here we'll try less than a year, 1 to 2 years, and then more than 2 years. All right, let's try that. Okay, let's give that one a shot. Okay, well, this is pretty much what I expected. In most of my other math classes, the majority said 1 to 2 years. Now, that's getting to be a fairly long time, but that's okay. Even if you're a little bit rusty, these concepts that you've seen before will come back to you as we go along. So the first chapter is mostly material that you should have seen before, and now is your opportunity to refresh your memory. And once that gets started, the process of seeing math again, you'll see that a lot of it will come flooding back into your memories, and you'll be getting used to again thinking about math. And that's exactly what we hope for. So it's kind of like any other activity that you've not taken up for a while. Like it's kind of like, imagine you haven't been out running in 6 months. Yeah, it's going to take a while to get used to it again, but pretty soon you'll find yourself getting back with it and then benefiting from it. Okay, so that's that. All right, now let's go back to the syllabus. What else do we need to know? I think we're almost. How about grading? Yeah, people care about grading. Yes. So, like I said, we're going to do a lot of practice problem sets together because we need the practice. But ultimately, the grading will come down to 3 exams. There'll be 2 midterms and a final, which you'll do at home, of course, because there's no in-person classes. You might be taking in-person classes for other areas, but not this. In fact, the school has made it kind of clear to us that they would prefer that only certain majors be on the campus. So you might be in one of those majors. I don't know. In fact, I'll tell you what, let me do one final poll before we get started. We don't want to spend the whole day doing polls, but just out of sheer curiosity more than anything else, I'm going to ask you, the question is, are you taking any in-person classes? Okay, well, this is just a simple yes or no. All right, let's do that one. This is just for my own knowledge. I'm just wondering. Okay, well, that's interesting. The overwhelming majority of you are saying no. Okay, so I think the reason why the numbers are so different from one class to the next is because I have different majors in my different math classes. So in some of my classes, I have a lot of performing arts majors. And so it stands to reason that they'd be taking in-person classes. But for everybody else, pretty much it's forget about it, because there's really no reason why we can't do this online. I mean, it's not ideal, but it certainly is. It's so far, I think it's working out reasonably well. So I think they would rather not have us come back until they're sure that it's safe. So for this semester, at least, many of our classes will still be online. It might be different in September. I don't know. I'm sure that's what they're hoping, but we won't know for a while, I guess. All right. Anyway, so now let's just take one more quick peek at the syllabus for the topics that we'll be covering. And some of them should look very familiar. So what are we actually doing here? We're doing functions, we're doing linear functions, we're doing polynomial and rational functions, a lot of functions, if you notice, exponential and logarithmic functions, trig functions, and then finally we get to some other applied areas like systems of equations, sequences, probabilities, counting theory, and then finally our proper introduction to calculus. So we got a lot to do this semester. And by the time we're done, you'll have a very, very solid math background, even if you choose not to go any further. It's not likely you'll run into any situations where you need more math unless you're actually trying to work in that field. So I'll tell you what, why don't we do this? Let's get started. Let's take a look at chapter 1. And I'm hoping that as we go along, you'll realize that you do recognize most or all of this content, even if it's been a while since you saw it. Now, another thing I do want to mention this right up front. This is a very, very long class. You know that. It's more than 3 hours long. It's a double session, basically. So because of that, we're going to have not just one, but two breaks, two short breaks in the middle, just so that you have time to recover. Okay, since you're at home, you should have access to munchies and caffeine maybe if you need it, just to keep going for the whole period. Because I don't want anybody passing out in this class, which might happen if you have to sit here and listen to 4 straight hours of math. So yes, as we go along, we definitely will have some breaks. Don't worry about that. But right now, why don't we get rolling? It's after all Wednesday morning. Now, whether you want to admit it or not, this is when your thinking is at its peak. Okay, right now, this is the best time to absorb complicated topics. All right, late at night, maybe not so much. So this is it. These are your prime thinking hours. Now, does anyone have another class after this? No, pretty much very few classes at Purchase meet on Wednesdays. So this is probably it for you. And that's good. I think that works out very nicely. All right, so let's start. We're going to start with this concept of a function, which you've all heard of before, but possibly you've started to forget exactly what it means. Now, you noticed in the chapter titles, a lot of the topics in this book, at least in the first few chapters, are all some types of functions. So this is obviously a critically important topic. And so we're going to start by looking at different functions and their properties. So we're going to start by making a distinction between what's called a relation and a function. Now, I'm sure you remember what an ordered pair is. Let's say you're looking at a graph using the XY coordinate system. Okay, so let me randomly pick a point like 1, 2. What does that even mean? That means that the X coordinate is 1 and the Y coordinate is 2. The logic here is that they're listed in a specific sequence where it's understood that the first term represents X. Let me draw that better. And the second one represents Y. All right, so these are referred to as ordered pairs because the order makes a difference. In other words, 1, 2 is not the same point as 2, 1. Okay, so 2, 1 would be down here somewhere. Okay, X would be 2 and Y would be 1. All right, so these are the XY coordinates, which you're very familiar with. Sometimes these are known as Cartesian coordinates. You may have heard that name. After their inventor, the famous philosopher / mathematician, Rene Descartes. Okay, yes, you may remember this. Now, by the way, the history of math is actually quite interesting. It may not seem like it, but it is. So whenever we get an opportunity, I think we should briefly step aside and acknowledge the contributions of these people to math. So Descartes, lived in 17th century France. He was a philosopher, he was a theologian, and he was a mathematician. And he made a lot of important contributions to all three fields. But he's best known for one of his most famous sayings as a philosopher, which you may have heard of. It goes like this: I think, therefore I am. Ooh, you must have heard that one before. If not, you can see that's pretty deep. Okay, I think you'll agree that's a very intense little statement there. This is one of his most famous sayings. And remember, he's doing all three of these things. He's a philosopher, he's a theologian, and he's a mathematician. He invented these XY coordinates that we've been using ever since. So ordered pairs are listed in the following way. In each case, X is first, Y is second. So any group of ordered pairs is referred to as a relation. Okay, now not relationship, by the way, it's just relation. So for each Y, there's an X. Okay, so there doesn't need to be any particular pattern to these numbers. As long as we have a set of ordered pairs, that set is known as a relation. But is it a function? Now that's the interesting part. All functions are relations, but not all relations are functions. Okay, there are certain rules that have to be followed for a relation to be considered a function. What are those rules? Now, here's a simple example. This is our relation. We have three ordered pairs. And in fact, if you wanted to, you could actually draw these just to get a feel for what they look like. We have 1, 3, let's say here. 2, 5 would be here. And 3, 7 would be here, let's say. Those are our points. Okay, now we're going to introduce, by the way, in any discipline, as you know, there's a lot of vocabulary that you have to learn, especially in the early stages. So we're going to go through a few of those key terms today. And like I said, many of them should be already familiar to you. For example, here's one that you might not have thought about for a while. Domain. What is the domain of this relation? Well, the domain is simply the set of all the x's. Okay. Okay, so the domain of this relation is simply a set that contains all of the x values. Now, if there is a definition for the x values, it stands to reason that there's a definition for the set of y values. Here's the big question. Does anybody remember what the y values are called? Yes, we have one person who knows. That's right. The y values. Oh, nice. Yes, we got more than one. It's flooding back in your memories, isn't it? Yes. The range. That's right. You're all right. The range. So the y's, the set of all the y values, is referred to as the range of that relation. Okay. So we have, for every relation, we have a domain and we have a range. These are the x's, these are the y's. All right, now, with this in hand, we can now formally define what we mean by a function. Okay. A function is a special type of relation. It's a special case. Okay. And with a function, it assigns a single value to each element in the domain. Now, in order to qualify as a function, there cannot be any repeated elements in the domain, but there can be in the range. So we're going to see some examples. Don't worry, this is a very abstract definition. We're going to see some examples so you get a better feel for what this actually means. Okay. Oh, here we go. We have a question. I think you can enter it into the chat room. Oh, how does that work? I'm not sure, quite sure. Somebody raised their hand. I'm not quite sure. I think you're supposed to type your question into the, here it is. Yes, that's exactly right. For each x, there's one and only one y. That's what it means to be a function. All right, we'll see this on the next slide. So let me show you a picture of this. And I find, that it helps to understand something if there's a picture. So here we have the domain, and here's the range. Each x is assigned exactly one value of y. This diagram, by the way, is commonly used in math. It's easy to see what's going on. These are just meant to be two sets, and these arrows mean that one has been assigned to 5, 2 has been assigned to 15, and 3 has been assigned to 10. You can hardly see it, but the arrows are pointing this way. So what we need to do now is see some examples where our relation is not a function. What could cause it not to be a function? Okay, well, for one thing, this one doesn't work because you notice what's happened here. X was assigned to 2 different y's. Okay, in other words, 1 is assigned to both 5 and 10. So let's see if we can draw a picture of this and so we can visualize what the problem really is. If you were to actually draw a picture on the XY coordinate system, you've got when x is 1, y is 5, and when x is 1, y is also 10. When x is 2, y is 15. And when x is 3, y is 10. Whoops, not there. Hold on. Okay, so the issue here is right here. For the same x, x equals 1 is assigned to 2 different values of x. Okay, that's a problem. That means that each x does not have one and only one y. So if you remember it from high school, you might remember seeing a function or a graph that looks something like this. Yes, it's sometimes called the pencil. It can also be called the vertical test. That's right. In other words, if you drew a vertical line through the x coordinate, if it touches this graph twice, that means this is not a function because x has 2 different values of y. But on the other hand, if you have something like this, that's not a problem because no matter where you put your vertical line, it's only going to touch the function once. So we have what's called the vertical line test that can help us to determine if this is a function or not. We'll see this later on too, but it does exist, and it's just a way of visually imagining whether or not this is a function. And all you have to do is imagine you've drawn a straight line, a vertical line, and if it ever touches that graph twice, then we do not have a function. It's still a relation, but it's not a function. So this is a relation, but not a function. Now, the other case that can cause problems is this one. Ooh, what happened here? If you notice, x has not been assigned a value of y. Therefore, this relation is not a function. And so those are the two potential problems that can exist. So basically, remember, as long as each x is assigned to precisely one y, we're good. If some of the x's are missing, or if some of them have been assigned to two or more y's, then we do not have a function. Then what we have is called a relation. All right, now, here's a fun example. It turns out, I mean, this is, of course, you normally apply this to numbers, but here's an example where we have a function which is not assigned to numbers necessarily. What we have here is sizes of coffee and prices in Dunkin' Donuts. So in each case, we have a size and a price. And if you notice, this could be considered a function. How do you know that? If you were to draw a picture of this, or in this case, we create a chart, and you can see each size, or x, is assigned exactly one number. So this table can be thought of as a function because each x is assigned one y. Now you notice how x is the size and y is the price, because if you recall, in these cases, we say that y is the so-called dependent variable, and x is the independent variable. Which simply means that y depends on x. In other words, what we're saying here is that the price depends on the size of the coffee. Of course it does. How else could that work? When you walk in the door, they don't just randomly assign prices. There's a rule here, and that rule is what we mean by this function. Okay, so this qualifies as a function. It's kind of an odd function, but it does work. Okay. So how about this one? Is this a relation or a function? What do you think about that?
A relation.
Well, actually, it is a relation, but it is also a function. Yes, Julie is correct. It is a function. Here's why. Even though two people have the same birthday, that's fine, but each individual only has one birthday. Exactly. That's the point. Yes, it's possible for two people to have the same birthday. If you think of these as x's and y's, each x is assigned, though, to exactly one y, and therefore this must be a function. Okay, it's possible for two x's to get to the same y. That's okay. That's not a problem, as long as each one of them individually only has one y. This is what you're basically seeing here. Actually, no, sorry, I did that wrong. So in other words, these two are mapped to y, but that's fine because each one is assigned uniquely to one value of y. So this is a function. All right, I'm not sure. So the domain, this is the domain of that function, and this is the range. Okay, same thing up here. This circle on the left is a domain. And this is the range. Okay. How about this one? Now, sometimes it's a little easier if you draw the picture. Let's take the X's and the Y's. There's 1, 1, 2, 3 here. Over here we have 1, 2, 3, and 5. And if you draw the connecting arrows, 1 is assigned to 1. It is also assigned to 2. 2 is assigned to 3. And 3 is assigned to 5. That's right. Now you notice what's happening here. 1 is assigned to 2 different Y's. And therefore, this is not a function. It's still a relation, but it's not a function because X equals 1 was assigned to 2 different values of Y. And again, if you were to try to plot something like this, what you're going to see is that you've got 1, 1 and 1, 2. And since a vertical line test shows that they're both set equal to 1, this is not a function. Let's see, it looks like I've got a graph here for that already. Oh, right, sure. I just drew the circles for you. And you can see there's the issue right there. Oh, so therefore this is not a function. But it is still a relation. And remember, any set of ordered pairs is a relation. Okay. Now, we're going to go on to a new idea. We're going to learn or remember, if we've already seen this before, how to do something called evaluating a function. In other words, what we're trying to do now is calculate a specific value. Okay, so what we're going to do is write out a function, not just as a list of ordered pairs, but as an algebraic expression, which is what you're going to see most of the time. Here's a simple example. What if your local gas station charges $3.65 for a gallon of gas? The function here is, how much am I spending on gas? Well, X represents the number of gallons that you've bought. So clearly, if I buy, let's say, 10 gallons of gas, then I must have spent $36.50 on gas because I've replaced this X with a 10 to come up with a specific value, which is $36.50. And if you notice, this is written as f of 10 equals 365 times 10. So these are the X's. If I replace this with 10, this becomes a 10, and suddenly I have a specific value. And so what I've done is I've evaluated this function when X equals 10. And in principle, I can replace that X with any number I want. Now, clearly here, it can't be a negative number. Yes, that's a good point. I'm glad you mentioned that because we'll see this later on. Anyway, f of X equals 365. You can also write this as Y equals 365X. This just means that whatever this is, it's a function of X. So we usually use the letter Y to represent that. These both mean the same thing, okay? So you'll see these used interchangeably throughout calculus and pre-calculus and all math for that matter. Just remember, these both mean the same thing. For certain applications, it's more convenient to use the f of X. And for certain applications, it's more convenient to use the Y. It's good to have both of them to choose from. In fact, you'll discover as we go along, in math, there's usually more than one way of expressing the exact same concept. Just like in English, there's always multiple words that mean the same thing, aren't there? Like, for example, is there only a single word that means good? No, I'm sure you can think of others. Like what? Wonderful. Is wonderful a synonym for good? Kind of. It's not precisely the same. So the analogy breaks down a little bit here, because with English, the words aren't necessarily literally identical to each other, but here, these two do mean literally the same thing, f of x and y. All right, here's another one. Ooh, now we're getting to some tricky territory. In fact, this is your first challenge of the day. Why don't you take out a pen and paper and determine the value of this function when x equals 7. Okay, this will get you some good practice. Now remember, it's a cold winter morning and you haven't had a math class in a while. This is a great way to get back into the swing of things. All right, so let's see what you come up with. Here we go. Okay, we have one vote. We have another vote. We have a couple of votes. Okay. So tell you what, why don't we show you what exactly. All right, here we go. We're getting a lot of 35s, which is good because that's the answer. Now, if you didn't get it right, let's take a step back and make sure we understand what just happened. What you're doing is you're squaring the 7, and then you're subtracting 3 times 7, and then you're adding the 7. Now, if you break this down into each component term, the first term is 49, second term is 21, minus 21 that is, and the third term is 7. And if you add those together on your calculator, you'll see that it's actually 35. All right. So if you got it wrong, that's okay. It's been a while, you've gotten away from it. Just try it again. Plug those numbers in your calculator and see what you can come up with. Yep, it's 35. Okay, no, we got to brush off the cobwebs. PEMDAS, yes, it works very well, does it? Yes, it does. All right. Now, sometimes you run into these abstract cases where you're replacing x with actually just a letter. You'll see a few of those cases as we go along, and then it's exactly the same. You literally just replace your x with that letter. This letter is some unknown constant. We don't know what it is. When we find out what it is, we can find the exact value here. But in a case like this, you would just replace the x with an a, and then you would just leave it like that because you have no further information. So if you run into a case like this, do not panic. It's not meant to have a specific answer. It is 3a. So no matter what 3a is, we plug that in and we add 7 and we'll have our answer. All right. So solving functions. Now, evaluating is one thing. Solving is a little bit different because let's say, for example, I have this function, x squared minus x minus 12 equals, I'm going to set that equal to 0. By the way, this is where Symbolab will come in very handy. Let's go to Symbolab. If you have your computer open, oh my God, there it is. Oh no, that's not it. Here it is. So if you type in Symbolab, now what you need to do is type your function right here. And this will take a little getting used to. For example, oh God, I lost it. It's x squared. X, now use this box. No, sorry, I'm still getting used to it myself. Type the x, use this box to create an exponent, okay, minus x minus 12. So let's hit the go button. And then here's where you ask for the graph. It's not, I mean, the website isn't as efficiently set up as it could be, but if you hit this graph function, this is what it's looking like. Now, what are we interested in? Let me copy this onto a Word document real fast. Copy, and then I'm going to paste it into here. And just so I can show you exactly what we're trying to do. So if you notice in the function, it says we're trying to find out where this function equals 0. So in other words, we're trying to find where it crosses the horizontal axis, because all along this horizontal axis, y equals 0. And so these are the corresponding values of x when y equals 0. That's what we're trying to identify. Okay, so we have one person is saying, is it minus 3 comma 4? Let's find out. Now, this is something you might not have thought about for a while. This type of equation has a special name. Any equation that has a squared term is known as a quadratic equation. And because of that, there will be two solutions. And you can see that from the graph, of course. There's two values of x where y equals 0. In other words, there's 2 points where the function crosses the horizontal axis. That's what we're looking for. What are the values of x at those 2 points? Well, you can kind of see them on the graph, but let's just do this mathematically. How do you solve for something like this? There's a couple of options that we have, and I'm sure you've seen these before, but maybe you haven't thought about it for a while. What you can do is what's called factoring. When you do that, you're going to end up with an expression that looks like this. Okay, so let's try that approach first. Now, in a case like this, now the m and n are constants. We're trying to solve for those constants. So what we need is to find an m and an n with two properties. Okay, it must be the case that m times n equals negative 12. And in addition, m plus n is negative 1. Because, and by the way, here, this might be worth reviewing for a second. If you have a number like this 3 is known as the coefficient of 3x. What is the coefficient of negative x? It is, in fact, negative 1. And while we're on the subject, what's the exponent of negative x? It's actually 1. Okay, yes, exactly. So in other words, with a number like this, x is the same thing as x to the first power. I just want to mention that because you might have forgotten. So this is referred to as the coefficient of this expression. And the exponent, there's an implied exponent of 1 as well. So what we're trying to do is find a pair of integers, as it turns out, where their sum is this coefficient and their product is this constant. Now, how do we find them? Well, as far as I'm concerned, the best way to do this is to write out all the integers that you know whose product is negative 12. Let's try that. How about 1 and negative 12? How about negative 1 and 12? 3 and negative 4, negative 3 and positive 4, 2 and 6, 2 and negative 6, negative 2 and 6. Is that all of them? Yes. So there's 6 pairs of numbers whose product is negative 12, but only one of them has a sum of negative 1. Which one is it? That's right, 3 and negative 4. So that means our factors are x plus 3 and x minus 4. Now, what I would like to do is show you a fun technique for proving this. It's something that you've all seen before, and it's been many, well, I wouldn't say many years, but it may have been a while. And I'm going to write this down, and you're going to say, oh, where has this been? I've forgotten about my old friend. Here we go. Oh my God. Now, who remembers what that stands for? Yes, go ahead. Oh, you can actually talk if you turn off your microphone, on your microphone.
It's first, outer, inner, last.
That's right. So yes, and Kristen has the same answer. Christian has the same answer too. Yes, you don't forget this, do you? Oh, here's a fun side note. A word like this, which consists of an abbreviation of other words, has a special name. Does anyone know what that is? I'll start it. Oh, we have somebody who knows. That's right. This word is called an acronym. I just thought I'd throw that in there for the fun of it. By the way, there's always words now, like a word like RAM is an acronym. RAM, what is that? Who knows what that word refers to? Well, you've all got computers in front of you. You should know that's a measure of storage. Your computer storage is measured in RAM, random access memory. That's exactly right. This is an acronym. Now, you might be shocked to hear this one. The word laser is an acronym. I don't remember exactly. Oh, somebody knows. Let's see what they came up with. Okay. Well, that's okay. No matter how you know it, you know it. The way you know it is irrelevant. As long as that knowledge is locked up here, you don't have to tell anyone. How do you know that? It's all that matters is that you know it. Okay. So laser stands for light amplified something, something, something. I don't remember anymore, but it is in fact an acronym. But anyway, let's get back to this. So if I take my results from before, what I want to do is multiply this out. I'm going to use FOIL on this technique. So I'm going to write out all the steps. First would be these two. I'm going to multiply x times x. Let's see. Outer are these two. That product is negative 4x. Inner are these two, 3x. And last would be these two, minus 12. So I combine these, and I come up with x squared. These give me negative x minus 12. Is this what we started out with? Yes, it is. So now, here's the interesting part. If x squared minus x minus 12 equals 0, that implies that this product equals 0, which in turn implies that each of these individually equals 0. And that means that x equals negative 4, negative 3 and 4. Those are the points on that graph right here. where the function crosses the horizontal axis. So we say that -3 and 4 are the solutions to this problem. Okay, these are the solutions to f of x. Okay. Now, since this is a quadratic equation, is there another technique that you could have used to find these solutions? Oh, yes, there is. And who remembers what it's called? No, this is not the greatest common factor. The greatest common factor means, like if you've got 24 and let's say 12, 12 is the greatest common factor because it's the largest value that evenly divides both of them. This is something different. Now, when we started out here and we saw this function, and you saw that it was a quadratic function, you might have said, you know, there's another approach we could have taken. That's it. Your old friend, the quadratic formula. So why don't we try that right now? And again, this is all, you know, this is all review, I hope, but good review. They are called the roots. That is exactly correct. They're called the solutions, and they're also called the roots of the equation. That is very true. Like I said before, in math, there's often many words that mean the same thing, and roots are one of the words that refer to solutions to an equation. Exactly. All right, see, it's all coming back in a flood, isn't it? It's all gushing back into your memory. You can't help it anymore. All right? You feel your brain sloshing around with all that knowledge that's gushing out of every which direction. So why don't we do this? Why don't we review the other approach we could have taken, which is our old friend, the quadratic formula. Okay, so that's our original function. So the quadratic formula, now first of all, in the most general possible terms, a quadratic equation looks like this. Okay, whoops. Okay, so in this case, a is 1. There's an implied 1 here. There's also an implied -1 here. So a is 1, b is -1, and c is -12. So what do we do with this information? The quadratic formula now, I think as I write it out, you're going to recognize that you remember it very, very well. Are you ready? Oh my God, where has this been? Okay, yes, you haven't thought about this. It's like I said, it's like an old friend coming to visit. You haven't seen this person in years, but they're still welcome in your home because you love them when you first met them. And so now we just plug in the numbers. We're going to have minus 1, plus and minus, -1 squared, -4, 1, -12, all over 2 times 1. So then that I'll bring it down here. 1 plus and minus. Now inside here, if you evaluate this, let me move this up here. Under the square root sign is actually 1 plus 48, 49, which of course equals 7. So we have 1 plus and minus the radical 49 over 2, 1 plus and minus 7 over 2. Now we can break this up. This actually means 1 minus 7 over 2 and 1 plus 7 over 2. So we're going to have -6 over 2, 8 over 2, and guess what we have? -3 and 4. And so, of course, these are the same numbers we had just a few minutes ago, but now we found them with our friend, the quadratic formula. Okay, so this wasn't new to anyone, was it? No. It may have been a while, but you've seen it. Now, I did want to point out something over here. You see the square root of 49. I just want to briefly remind everybody that this 49, along with several other numbers, let me draw up a list. There's a group of numbers in math that have a very special name. The numbers are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Yes, already somebody knows. These are called, yeah, we're going to plug these back in. Hold on one second. These are referred to as perfect squares. Why? What do you notice about these? Because the square root of each of these numbers is an integer. Okay, so here's our classic example. Perfect squares have very important properties. Every one of these has a square root, which is an integer. And that comes in mighty handy when we're using the quadratic formula. Now, what we're going to do next is this. We're going to prove that our answers are correct. All right, so in other words, we've just demonstrated that the solutions are, so the original equation was x squared minus 12x, it was minus x minus 12. So we'll start with 3. Let's see if 3 works. Oh, wait a minute. No, I did something wrong, didn't I? Yeah, wait a minute. Hold on a second. That's why, because I got these two backwards, of course. This is minus 3, and sorry. No wonder. All right, that makes a bit of a difference. So we're going to demonstrate that both of these are, in fact, the solutions of this equation. We want to prove that this is true, so we'll start with this one. Minus 3 squared minus a minus 3 minus 12 equals 9 plus 3 minus 12 equals 0. Good. So this one works. How about 4? 4 squared minus 4 minus 12 equals 16 minus 4 minus 12, 0. So they both work. So we not only found the solution in 2 different ways, but we also demonstrated that it works. We proved it. And now the last step is to go back to the graph, which I have here. And you can see we have 4, 0 and negative 3, 0. And those were my solutions. The x's are the solutions to this. X equals 4, x equals negative 3 are my solutions. Very good. Now, by the way, there's a special name for this type of graph. Let's see who remembers it. I'll give you a hint. It starts with a P. There it is. Yes, parabola. It's a parabola. We'll discuss this in more detail later on. This is known as a parabola. Just as an aside, I just want to remind you, but we'll pay much more close attention to this very soon. We'll be analyzing parabolas in very great detail as we go along, because they often show up in applied situations, especially in the field of economics. We tend to run into this quite a bit. Now, if you've had any economics classes, you might recognize that often total cost functions might look something like this, or average total cost functions, I should say. All right, now, functions can be classified in different ways. Okay, so in other words, once we've established what a function is, there are different kinds of functions. So we're going to introduce the concept of a one-to-one function. Now we know that with a function, each element of the domain is given precisely one value in the range, but there can be multiple repeated values in the same range. We saw that with the birthday example. So if we have names and birthdays, the function that assigns names to birthdays is a function, as we saw earlier. In fact, let's go revisit it. Okay, so it's a function, all right, because each person gets one birthday, but some people can, there can be birthdays that have more than one person attached to them. So in other words, there's two people here with the same birthday. So therefore, this is not what we will call a one-to-one function. A one-to-one function means that for each x, there's precisely one y, and for each y, there's precisely one x. So let me show you what would be a good example of that. How about social security numbers? Now that's a different matter altogether, because let's say we have names, and then we have Mary and we have Bill. And let's say the first one is 11111. Can two people have this one as their social security number? They cannot. So that means that unlike with birthdays, where you can have two people with the same birthday, you can't have two people with the same social security number. So let's say the function looks like this. So this is not only a function, it is a very special kind of function. It's referred to as a one-to-one function. And that simply means that each y is only associated with one x. Now, we already know that each x is only associated with one y. That's understood because this is a function. But now if in return, it works both ways. In other words, each y only has one x. That makes it one-to-one. All right, so now this has special implications, as we'll see. So here's a good question for you. Is the function, all right, I'm going to wait till we're all ready. Man, I see a lot of camera shy people in this class. That's okay. You don't have to be on camera. I'm just looking for shocked faces. I want to see if everybody is horrified or if they're doing just fine. It's easy to tell in the classroom. Like everybody, you can see they're right sitting in front of you. You can tell if people are following or not, or if they're getting scared or not. But here it's a little trickier. But so far, I'm not seeing anybody passed out, and that's good. So, so here's an example. Oh, no, that's fine. No, you're not required to be on. I just wondered if anybody was running into trouble and were reluctant to say so. You can always stop me if you think I'm going too fast. And you say, listen, could you go back? Could you do this again? Oh, you know what that reminds me? I almost completely forgot about this when we were going over the syllabus. I was supposed to remind you that these sessions are all being recorded. Now, the tricky part, though, is that Moodle isn't really well suited for storing videos. It doesn't seem to have enough storage capacity. So as a compromise, what we're doing is this. All of my SUNY Purchase videos are found in my YouTube account. Now, you're all familiar with YouTube. Of course you are. So what you need to do is you come here to my account. And as far as I know, if you type in my name, that will take you right to my page here, or my channel, it's called. And what I've done is I've created a series of what are called playlists. Yours is set up, but it doesn't have any videos in it just yet. If you check on the playlists, each one is for each class. So in other words, you don't want to have to sort through millions of videos. As soon as we're done today, your playlist will appear here in this list, and you'll go right to it, and you'll say, oh, here's our videos. Okay, and you can download it and watch it to your heart's content. Any time, number of times you want. And then, so this way, if you've missed something, or if you just want to, you know, see it again, I mean, that's fine. You can do whatever you want. They're yours to use. So, you know what I've discovered too, almost by accident, if you see a YouTube video that you like and you want to not lose it, if you click that little thumbs up button, it'll actually keep track of it. Like over here, these are all the videos where I use the thumbs up. Every single one of them is in this playlist. So if I want to like watch that video again, I saw it 2 weeks ago, about the Yankees, let's say, it's still there. Oh, all right. So let me remind you what one-to-one means. So anyway, so the point of it is that all of this, as soon as we're done, the videos, it might take a while because it has to be processed into an MP4 format, but it will eventually show up in this playlist and you can find it anytime you need it. So yeah, the one-to-one means this. Let me show you a picture of this. It means, let's go back to this setup with X's and Y's. Let's say you got 3 numbers, 1, 2, 3, 4, 5, 6. So one-to-one means that each X, of course, we know that each X goes to one Y, but each Y only goes to one X. In other words, you're not going to have something like this. Okay, so in other words, this is a function one-to-one. This one is not one-to-one, but is a function. So we'll call it is a function, but not one-to-one. They're both functions because each X only goes to one Y. But here you notice 2 X's are associated with the same Y, which is fine for a function, but that means it's no longer one-to-one. So I really think what you might want to do, to help yourself remember this, think of this as social security numbers. And think of this one as birthdays. I really like that analogy because obviously each person can only have one birthday, which means that this is a function. Each person can only have one social security number, which makes it a function, but more than one person can have the same birthday, which means this is not one-to-one, but each person, can only be one social security number for each person. You can't have 2 people with the same social security number. So this is one-to-one, whereas the birthdays are not. Okay, does that help?
Yes, thank you, Professor.
Okay, good. All right, I like this analogy a lot. If you forget, just think of social security numbers and birthdays. All right, very good. So anyway, here's a challenge question for you. While this one is clearly a function, is it one-to-one? Now this graph looks like this. Let me help you out here. Now remember, one-to-one means that, yes, here we go. Okay, we have a vote for yes. Okay, now let's use this approach. Let's say we have 1, and -1. What value are they assigned to in y? Oh, okay. So in other words, 1 squared is 1, but so is -1 squared. So that means it is not 1-to-1. It's a function, all right? Each x goes to 1y. In fact, remember we talked about the vertical line test. No matter where you put a vertical line, you're only going to touch the function once. So the vertical line test shows that this is a function. But what we can do now is introduce the so-called horizontal line function. Now watch what happens. If I draw a horizontal line through here, you can see that when x equals 1 or when x equals -1, y is 1. And so that means not a 1-to-1 function. Okay, so we can use vertical lines to test if this is a function, which it is. But the horizontal line test means, oh, if we touch this function or this function twice, it is no longer 1-to-1 because both x equals 1 and x equals -1 are associated with y equals 1. Okay, so in other words, f of 1 equals 1, f of -1 also equals 1, not 1-to-1. Okay. All right. What about, I think there's another, yeah, you can see, and so this is y. Oh, look at that. And not only that, but look at that. 4 is associated with both -2 and 2. So this is definitely not 1-to-1. Yes. And again, you can try out the horizontal line test. Too bad. It fails. This is not 1-to-1. So yes, we're going to introduce now the so-called horizontal line test. If any horizontal line touches the curve more than once, then we do not have a 1-to-1 function. All right, now, but what about this example? Let me hold on a second to make sure everyone's caught up. Okay, I don't want to keep you in suspense. Are we ready for the next example? All right, good. Watch this. Is this one 1-to-1? Now, this is a straight line. Remember, the equation of a straight line is y equals mx plus b. M is the slope. B is the intercept. And we formally define the slope as delta y over delta x. So this is the function the intercept is 7. Whoops, I wrote that backwards, sorry. That's 0,7. But you notice it's a straight line. So no matter where you put the horizontal line, you're going to get only one intersection with that line. So the answer is yes. Okay? No matter what x is, there's only one y that goes with it. And no matter what y is, there's only one x that goes with it. So a straight line, by definition, are 1-to-1 functions. Okay, it has to be. Like I said, you can visualize all these horizontal lines rather. It's not possible for that horizontal line to touch y equals x plus 7 in 2 different points. So therefore, this does qualify as 1-to-1. Yes, the fact that it's linear means that it's 1-to-1. All right. And so there it is, right? So like I drew it out properly for you. And then just no matter where you put that horizontal line. Now, by the way, I'm drawing it very carelessly. It should be a parallel line. But actually, I guess it doesn't really matter. No matter where you put it, as long as it's a line, it's never going to cross this function more than once. All right. So you know what? It's 9:30. Now I did mention before this is an unbelievably long class. It's like a marathon basically. So let's have our first break of the day. You're going to need to get some refreshments, I'm guessing. Either that or just let your brain cool off for a few minutes. So why don't we knock it off for about, let's say 15 minutes should be enough to get some munchies, caffeine, whatever you need. And when we get back, you'll be ready to go and do some more of this fun stuff. So, all right, let's do it. Let's come back in a bit. Maybe I'm thinking 15 minutes should be enough for everybody to get all the munchies they need to get back into the swing of things. Because by now our glucose levels are getting pretty low, aren't they? Yes, they are. All right, so let's do it. Uh, all right, I guess we can get going again. What I do want to do though is open up this first practice problem set just to see how far it goes. I've forgotten exactly how much material it covers. Let's see, we've got, oh, those are easy. Let's see, what else do we have? Practice problem set number 2. All right, so at the rate we're going, we probably will have finished enough material to at least do these first 2 practice problems by next week. Now, these are not to be collected. This is just for getting some more practice with these concepts. So what we should probably do is every week, we should do at least 1 or 2 practice problem sets based on the week before, just to make sure that we really understand what we're doing. Okay, so this week, it looks like we'll be ready to do the first 2, and then we'll carry it on from there. All right. And then that way, obviously by only meeting once a week, that makes it a much more intense class. And we do need to get some more practice. So this is the best way to do it, I think. Well, so where did we leave off? All right. Now, the vertical line test, I did already mention this. The vertical line test is designed to tell us if we have a relation which is not a function, because that would mean that each each x has been assigned to more than one y. So for example, let me just show you again the example I showed you earlier. If we had a graph like this, and you'd run into this every so often, it's basically a sideways parabola. Then the vertical line test would tell us that for the same x, which is here, let's say this is x equals 10, we have, let's say 10 comma 5 and 10 comma negative 5. And so that means that we've got an x with 2 different y's. That would be the equivalent of having something like this. Here's our x, here's our y. And you can see that 10 has been assigned to both of these. And we've already seen that that means that this is not a function. All right. Now, we're going to be looking at some different, as I mentioned before, there are many different kinds of functions. And so we're going to look at some of the more important ones right now. And of course, some of these are really simple. Some of these not so much. All right. So let's say, for example, here we have a few. Let's see how, oh my God, there's quite a few of them, aren't there? That's all right. A few of these are, most of these are fairly straightforward, but a few of these are actually quite complicated. So we'll start by looking at the so-called constant function, where literally all you have here is y equals some constant. So let's say that the actual function is y equals 10. That means you have a horizontal line. Now, based on the vertical line rule, this is a function because this vertical line only touches the function once, but the horizontal line, if you drew a horizontal line that coincides with y equals 10, you'll see that we have for an infinite number of x's, or an infinite number of x's, are assigned to y equals 10. And therefore, while this is a function, it is not one-to-one. Okay, so because again, the idea here is that if you could imagine with this diagram, no matter what x we have, let's say here's our x's, 1, 2, 3. It doesn't really matter. They're all associated with 10. Okay, so this is a function, but not a one-to-one function. Okay, it's a function because all the x's are assigned to exactly one y, but this y is associated with multiple x's, and therefore it cannot be one-to-one. All right, and of course, yeah, I mean, here I've chosen x equals y equals 5. It's the same idea. It's just a horizontal line. By the way, just to refresh our memories, what is the slope of this line? Remember, the slope is delta y over delta x. Well, what do you notice about y? Y is not changing. Y is a constant. So therefore, no matter what points we pick on this line, while x is changing, y is never changing. Therefore, delta y is 0. Yes. This slope would be 0, exactly. No matter what delta x is, the numerator will always be 0. And so therefore, that slope is 0. Interesting, yes. And while we're on the subject, why don't we think in terms of what a vertical line would look like? Let's say that we had a vertical line. I know this isn't what's listed here, but this is still relevant. Let's say that we had this going on. And now this would be, for example, x equals 5. Now we know from the vertical line test, this is not a function. But we still can define the slope. The slope would be, slope is delta y over delta x. So guess what? Here we have a problem because delta x is 0. It never changes. So the slope is delta y over, now what problem do we have here? The dreaded division by 0. So this slope is undefined. Oh yes, that is the case, undefined. Sometimes you see it written as infinity, but that's not really technically correct. It's undefined because it involves division by 0. Now, by the way, I do want to mention one more thing here. I have discovered a handful of very interesting videos about what we're doing here, which we will watch during the semester. And one of them is an extremely interesting discussion about why we can't divide by 0. Now, we all know that you can't divide by 0, but we might not be able to explain why. And I think you'll find it to be extremely interesting. There's no intercept. That's a good point. There's no slope. And there's also no intercept. Remember, intercept means that it crosses the y-axis. That's right, no intercept. It does not at any point cross the vertical axis. So it's a very bizarre relation. It is a relation, but it is not a function. Anyway, so yes, next week we'll watch some of these cool videos that I've alluded to, and especially the one about division by 0. I think you'll find it to be extremely interesting because the way they prove it is quite interesting, but also it's just a fun video. You know what I mean? It's very colorful. There's a lot of cool graphics. It's fun. Don't worry, you'll see it. Not this week so much. This week we're getting the ball rolling. But after this, from now on, just about every week, we'll have at least a few very cool videos that we can watch to help us make more sense of what we're doing here. Like there's another one that I'm going to show you, which is about the history of zero. So you might say to yourself, wait a minute, zero, hasn't it been around forever? No, zero was introduced into the real number system relatively late in history because, I mean, who would think that we need a zero? I mean, imagine yourself in the early days of humanity where all they cared about was counting up how many chickens they had or, how much money they owed somebody. So, yeah, zero is a relative newcomer to all of this. So next week we'll have that to look forward to. But anyway, in the meantime, let's get back to this. Then we have the identity function. All right. So in other words, think of this as y equals x. Now we don't need Symbolab to draw this one. What do you suppose it's going to look like? Well, it looks like I've already got it right here for you. Look at that. So you can see the slope is 1. Remember, the formula for a straight line is this. So since we have x here, that implies that m equals 1 and b equals 0. So the slope is 1, and the intercept is 0. And so you notice it passes both the vertical and the horizontal line tests. It's both a function, and we can say that it is 1-to-1. So we call this the identity function because no matter what happens, y and x are always equal to each other. So we have points on here like 2, 2, and 3, 3, and 4, 4, et cetera, et cetera. Now here's a fun one that you probably haven't thought about in a while. That would be absolute value. What does that even mean? Who remembers what that means? Oops. Uh-oh. What happened? Oh, no. I think I accidentally screwed up something. Oh, there we are. We're back. Okay. Okay, you can think of this as a distance from 0. But the bottom line here is what it really means is that the absolute value of x, let's see, how can I write this? I know what we'll do. The absolute value of x equals x. That's right. That's exactly right. If x is positive, and negative x if x is negative, which implies, basically this is just a fancy way of saying that the absolute value of x is always positive. So, but what does this thing look like? Now, by the way, why do we even need this? Well, for certain applications, it turns out that we don't really care about the sign. We just need the magnitude. And so we often take the absolute value when we want to get rid of the sign. Like here's an example. If you remember from high school chemistry, remember pH? What does that mean, pH? Like, for example, if the pH of a liquid, oh, okay, we have somebody who remembers. That's exactly right. So I believe the cutoff point is 7. Less than 7, that means it's an acid. If it's greater than 7, that makes it a base. I think water is 7. Yeah. Let me just confirm that. It's been a while since I was in high school. Oh. All right. Now, the reason why I'm mentioning this is because the way the scale is calculated, the pH numbers are actually negative, but we use the absolute values. Okay. other words, we don't say that the pH is -8, even though technically it is. We just say 8, and that means that this is a base. Okay, so maybe you didn't remember that, but it's basically what it refers to as the concentration of God, I've forgotten already, of something in the liquid, but the numbers are actually technically negatives, but we just ditch the negative sign. So what we're actually doing here is we're using absolute values. Okay, so I just wanted to throw that out there. All right, now what does this thing look like? Oh my God, how cool is that? The absolute value function is a big V. So is it one-to-one? No. And here's why, because as you can imagine, if X is 1, then Y is 1. If X is -1, Y is also 1. So you see, if you use this diagram, for X's, they're both associated with Y equals 1. So while this is still a function, it is not one-to-one. Oh no, what did I do? There we go. Oh, I'm sorry. All right, I'll slow it down. Thank you for letting me know. I can't tell because I'm not I don't see you. You're not right in front of me. That's one of the awkward things about online, is that I really can't see how everybody's doing, especially when there's no cameras. All right, so if you need me to slow down, you can say so, and I will certainly do so. All right, so yes, I like these little diagrams. It's easy to see, but obviously we're failing the horizontal line test. So while this is a function, because it does not fail the vertical line test, obviously, so this is not one-to-one. Also, if you notice, we can't have, oh, here we go. Let's see, what do we have? All right, oh, for God's sakes, I keep hitting the wrong buttons here. Yes, somebody raise their hand, go ahead.
Apologies for the interruption, but I was wondering if you could maybe go to slide 75 when you're done explaining this.
All right,
Thank you.
yes, I can.
Thank you.
This one? All right, yes, go ahead, yes. Absolutely. Don't worry about it. Just say it. Just go ahead and tell me what you want to do, and I'll do it. It's like I said, this is one of the really big problems with being online. I literally can't tell if I'm going too fast or not because I can't see you. Okay. All right, let me know when you're ready. Okay. All right, fine. Good. So yes, here it is. So if you notice here, you notice how it's not possible for Y to be negative. So in this case, let me just add this to the slides. The domain of this function, and we'll discuss this later on in more detail, is the entire real number line. Okay, so we might as well discuss this right now. This is meant to indicate that I'm including all the values from negative to positive infinity. Now, if you recall, the real number line is often illustrated like this. You've got all the numbers, they go up to positive infinity and down to negative infinity. But the range starts at 0 and goes up to positive infinity because Y cannot be negative. So X can be anything in this function, but Y cannot be negative. So we say that the domain is all real numbers. And this one, oh, by the way, I just realized I did this incorrectly. I'll tell you why. With this notation, we're supposed to use a bracket if we are including this 0, which we are. The parentheses are applied to infinities. If, for example, I did not want to include the 0, I would have a parenthesis here, but because I want to include it, I'm going to use a bracket. The bracket indicates that 0 is included in the range. And also, just a reminder, these things in math are called brackets. All right, and while we're discussing this, these guys in math are referred to as braces. That's right, braces, like the ones you had on your teeth when you were 13. Braces and brackets, and of course, these are parentheses. Everybody knows that. So yes, so here though, they have a specific meaning. So when you use intervals like this, the square bracket indicates that number is actually included. If I had a parenthesis here, that means I would not include the 0, but I would have everything after that. Okay, so just to make sure that we understand the notation. Okay. All right, are we all set? And you can see why. I mean, when you look at the graph, you can see that at no point does this function cross through the horizontal axis. So the y's will never be negative. And of course, that's because of the way this function has been defined. All right. Now, this we've already, of course, discussed earlier. A quadratic function has this form. We have to have an x squared term. So what that implies is that now the a, b, and c are constants. The only thing we have to note here is that a must not be 0. Otherwise, this term drops out and we end up with a linear equation. So the only constraint on this is that a cannot be 0. And this is illustrated with a parabola. Okay, remember what a parabola looks like. It's basically, you can think of it as a bowl, okay? And by the way, a parabola can also be facing down, depending on the signs of A, B, and C. These are both parabolas that we could run across. These would both represent a quadratic function. Okay, so we're going to look at x squared minus 2x minus 15. Now, we don't need to go to symbol lab for this one. I've already got it written up in the notes. But we're going to see that it's facing up. Ah, there it is. In fact, I actually had a teacher in high school who, in a case like this, referred to this as holding water. Have you ever heard that before? Holding water. You can see why, because imagine if you left this out overnight and it rained, yeah, it would be full of water. Okay, well, all right. That's kind of silly, but that's how, and then the upside down ones were said to be not holding water or something like that. So you can see it is in fact a parabola, and it cuts through the axis twice, the horizontal axis, at these 2 points. It looks like it's 5 and -5 from the graph. 5 and -3. But here, all that we really want to know is that it has a curve to it. And that means that the slope is not constant. Now, you might remember from some of your previous math classes, the slope can be defined as the slope you can draw a tangent line here, and the slope comes from this tangent line, and the tangent lines themselves are changing as we move along the curve. Here, for example, the tangent line is flat, which indicates that the slope is 0. Over here, the slope is negative. And over here, of course, from this point on, the slope is positive. And this is typical behavior for a quadratic equation. We have a range of slopes from positive to negative or negative to positive. One thing we do know is that the slope is not constant. Okay. Now, let's see what comes next. Oh, I see what's coming. The next one is the so-called cubic equation, where we have a term, an x cubed term in there. And of course, that's going to change everything. All right, so let's take a quick look at what a cubic function looks like. So this has 4 terms. Oops, uh-oh, did I go too fast? Oh, really? Delta Math. I'm not aware of this thing in Delta Math. Is it free? Oh my God. I used it. Okay. I'll tell you what, I'll look into it. I mean, I do have my own problem sets, but if this is something that can be used to get more practice, I'm all for it. So I wrote it down, so I'll check it out after we're done. But thanks for the idea. So if you use it in high school, it was probably free, I would have to imagine. But all right, anyway, so for the time being, let's take a look at this cubic function. Now, you can see it has an x cubed term, x squared, x, and d, and a constant d. And again, we have to make sure that a is not equal to 0, otherwise it's no longer a cubic. So this is the example that we want to look at. Now, it's hard to visualize what something like this is going to look like, but one thing that you're most likely to see is that unlike a quadratic equation, which crosses the horizontal axis twice, chances are this one will cross the axis 3 times because of this cube term. All right, so are we ready to see what it looks like? Let's resolve this mystery. Are we ready? Okay. Oh, okay, this one doesn't. Okay, it only goes through once. It depends on the signs of these terms, but it is possible for it to cross the axis 3 times if it has the right signs. This one did not. It only crosses once, but you can see it is a curve of some kind. It starts out, it grows very slowly, and then it starts to accelerate as we move along here. So the slope is positive throughout, but it is changing. In other words, the slopes are positive but declining. And up here, the slopes start to rise more quickly. In other words, these tangent lines are getting steeper and steeper, whereas here they're getting flatter. So here the slopes are positive, but increasing. And of course, we cross the axis once right here. This would be the solution to the equation. And of course, you can see that it is 1-to-1 because it clearly passes the vertical line test. I'm sorry, the horizontal line test. All right. So now we're going to get into some of the trickier ones, which have maybe stranger behavior. All right. So are we ready? Yes. Let's check out the next one. The next one is the so-called reciprocal function. So the classic example of this one would be f of x equals 1 over x. Now, you'll probably be a little surprised when you see this function. It's maybe not be what you're expecting, but you'll notice right off the bat, there's a bit of a potential problem here. The function is undefined when x equals 0, because that would lead to division by 0. So if something is undefined at 0, then the graph will not actually touch that point. In other words, the graph will never actually touch the vertical axis. It'll get close, but it won't quite make it. All right, so you'll see what I mean when we look at this thing. Now, the way it's drawn, I guess I should have continued it, but this curve will get closer and closer, the vertical axis and the horizontal axis, without ever actually touching them. So, wow. So as I said, it'll never actually touch the vertical axis. And in addition, it'll never touch the horizontal axis because there's no value of 1 over x will result in y equals 0. And so we say that these two axes, and we see this word, you'll recognize it right away, I think. Okay, here we go. It's a big word. Asymptotes. Remember, asymptotes is a line. So here you can see, here's the line, the horizontal axis. The function is getting closer and closer to it, but never actually touches it. Okay, same thing is true for both the vertical and the horizontal axes. The curve will get close, but never quite touch it. Okay, so all right, so that's what makes this thing unusual. All right, does everyone remember that word, asymptote? Just as a quick reminder, you might have run across this around the same time. Somewhat, yeah. You definitely saw it in high school. Okay, let me just throw in a quick graph here. Around the same time that you're introduced to, I don't think so. I mean, if you look at the Greek origins of the words, they must have something in common. In fact, you know what? That raises an interesting question. A lot of these math terms were invented by the Greeks. So let's do this. The Greek word asymptote means not meeting, not falling together. Okay, so they're showing you the evolution of this. But let's change that to asymptote. Oh, well, I guess that means it was created after the fact in the 30s by combining a, which means not, and without, and symptomatic. Oh, okay. Well, that's kind of disappointing. I thought it would have some other more exotic meaning, but it just means not. the A in the beginning means not, and that's all it is. But asymptote actually means not meeting. Lines are not meeting somehow, or not falling together, not coming together. I see. Okay. All right. Oh, so yes, what I was about to show you is another graph, and you might remember this. And if you do, see if you do. Okay, so maybe the drawing isn't perfect, but if you notice in this function, and let's say this function is going to be, let's see, oh, I know what it is. This function is actually x times y equals some constant k. Okay, so this function has a very special name, and you can see clearly the axes are asymptotes. This type of graph is referred to as a hyperbola. Oh my God, when was the last time you thought about hyperbolas? You can see it has the same properties. It's just that it's all restricted to the first quadrant in this case. And by the way, that means that we should review that idea too while we're thinking about it. If you recall from the XY coordinate system, it's broken up into 4 quadrants, but they're not maybe going in the same order you might expect. Those Roman numerals represent the quadrants. They go, for whatever reason, in a counterclockwise order. I don't know who came up with these names, but they decided to go counterclockwise. So this is the first, second, third, and fourth quadrant. All right, is that ringing bells? Yes, it is. You're all thinking, oh, that's right. How did I forget about quadrants? Now, while we're on the subject, there's, believe it or not, these lines actually have names. This x-axis is called the abscissa. Oh my God. And then this one is called the ordinate. Yeah, I'm sure these come from Greek words that mean something specific. But yes, the XY coordinate system, these axes do actually have names. Okay. I'm not expecting you to memorize them, but I just, wanted to throw that out there to see if you remember them or not. All right. So, man, all these wonderful memories that we're bringing up today. No, we're not going to. I just wanted to throw that out there just to remind you that these exist. I don't know if we're going to need these again. They'll probably show up somewhere in the future, where we have examples or homework problems where you're required to do something with this, like solve for it, for example. Yeah, hyperbolas have to be, because you can see if this implies that y equals k over x. So yes, this is indeed a reciprocal function. And if all the values are restricted to being positive. So this one, for example, it might be the case. And with functions, you can actually define a function to only be valid over a certain range of values. So here, for example, you might say that in this case, we're letting the domain be restricted to 0, infinity. And then that's what forces it to stay in the first quadrant. Okay, so if that's the case, now, why would that happen? If this is a real world example, you don't want to have negatives. Like if this is the relationship between costs and revenues or something like that, then you're only going to have positive values. So you formally define the domain to only be from 0 to infinity. Okay, all right, what comes next? when these functions get interesting, ooh, what about squared reciprocal functions? Now, this one is going to be a catastrophe, let me tell you. I'm sure, yeah, it would be, unless you've seen these recently, it'd be very difficult to visualize what this is going to look like. But what it does, though, is it guarantees that the range is going to be positive. Okay, we can't have a 0 because there's no value of x causes f of x to be 0. But everything, all positive numbers can be in that range. In other words, y can take any value in this positive range. X can be anything. The domain remains at negative infinity to positive infinity. So when you see it, though, you'll see it resembles somewhat what we were just doing. There it is. Oh, look at that. So you can see that it's getting closer and closer to the vertical axis, as well as the horizontal. It's not actually touching down here. So once again, both the horizontal and vertical axes are asymptotes of the function. One more thing, and I forgot to mention this in the last one. You notice how the function doesn't, there's a break in the function here. We say that the function is discontinuous. And the same thing was true with the previous one. I just forgot to mention it. Discontinuous means there is a break in the graph. And, you know, intuitively, and this is what I was told in high school, if you are trying to draw a picture of this function and you have to take your pencil off the paper at any point, that means the function is discontinuous. Okay, in other words, it does not, these two regions do not connect each other. And so therefore it's discontinuous. All right, so it's a very interesting. Now, when do we run into this? You never know. Every discipline is different. You may not run into this function in some disciplines, but you might see it in other cases. You might run into this, for example, in biology if you're trying to explain the growth rate of, let's say, bacteria or something. But in business, you might not run into this. Well, you're probably wondering, God, what else could there be? Oh, we've just started. All right, I'm sure, well. Yeah, okay. Still hanging in there, good. All right, very nice. All right, so yeah, it mentions it right here. There's a discontinuity in the graph since 1/0 squared is undefined. In other words, x 0 is not part of the domain. In other words, the domain is every real number except 0. And what we can do is write it in a very special way. In fact, let me do it here. The domain is the union of two sections What does the symbol mean? This is the union symbol. These are sets, by the way. We consider these to be infinite sets. So union comes from set algebra. The union means to combine two sets. So let's say, to make it a little simpler, let's say we had the sets 1, 2, and 3, and 4, 5, and 6, their union, A union B, would be the set 1, 2, 3, 4, 5, and 6. So we're going to see this notation sometimes when we're defining domains and ranges. And of course, the range x, y cannot ever be negative, and it also can't be 0. So we write it like this. Okay, so y can't be negative or 0. Okay, so remember that with this, our notation, the fact that this is a parenthesis means we're not including 0. If we want to include 0, we use the bracket. Okay. Okay, very nice. Now, of course, we'll run into these again and again throughout the course. We'll be being asked constantly to identify the domains and ranges of different functions. So we want to get some practice with it right now. Oh, I know what I wanted to do. A little bit of vocabulary, just because we'll run into it. If, let's say that x is, let's say, strictly less than 0, then we say that x is negative. But what if x could also be 0? Then we say that x is non-positive. I don't know if you've ever heard that terminology before. Non-positive means it can either be 0 or negative. And then if it's the other way around, this means it's positive. Or watch this, if it can be 0, we say that x is non-negative. Okay, so the thing about math is the language has to be extremely precise. All right, so now we're, obviously this is the time to introduce a lot of this language that we're going to need. And again, it's possible you've seen this before, but you've also maybe started to forget how this works. All right. Now let's look at the next case, the square root function. All right. Now, here's a quick, here's a good, let me throw this out there as a poll. Square roots. The square root of x is equivalent to raising x to what power? Okay, this is just to make sure you remember this. 0, 1/2, 1, and -1. Let's try that. It's been too long since we had a poll anyway. Let's do this. Ooh, people are reluctant to vote. What's going on here? Why aren't you? Usually people are eager to express their opinions in these polls. Oh no, what's going on? Here we go. Here we go. We have a contest now. All right, I guess that's everybody who wants to jump in. So the correct answer is X to the 1/2. So in other words, this symbol simply means you're raising X to the 1/2 power. So while we're at it, why don't we review a few of these important ones here? X to the 0 power is 1. X to the first power is X. X to the 1/2 power is radical X, or the square root. X to the -1 power is 1 over X. Negative exponents mean reciprocals. Okay, and then while we're at it, X to the -1/2 would mean 1 over radical X. That's probably all you need to remember for now. Okay. Oh, here's another one you might have forgotten. How about this one? What does that mean? 3. If I put a 3 here, what is that all about? Let me fix that. This is X to the 1/3 power, and we call this the cube root of X. Wow. When was the last time you thought about cube roots? No, it's probably been a while. That's okay. As long as you've got it fresh in your memory now. All right, so anyway, let's try to visualize what this graph is going to look like. Is it possible for y to ever be negative in this case? No. All right, well, let's take a look at it. And it's kind of a nice looking graph. Okay. Oh, okay. So, oh, by the way, of course, 1/2, these all mean the same thing. So it starts at 0, and then it increases. Now, if you notice, as we move up, as X increases, the slope remains positive. But it declines. So therefore, we say that the slope is, or I'm sorry, the function is increasing at a decreasing rate. Okay, so that's the language we would use there. The function is increasing at a decreasing rate. In other words, it's going up, but it's declining. In other words, it's the speed with which it increases is slowing down. It's kind of like you're driving along the highway and you're slowing down from 60 to 50 to 40 to 30. You're still going forward. You're just not going quite as fast. You're decelerating. All right, now, before you look at the next one, I'm going to ask you a question. In fact, maybe this will be a fun opportunity to take a poll. 2 polls. We'll do 2 polls. They're closely related to each other. Can we take the square root of a negative number? Yes or no? Oh, we have a lot of people who are unsure. I can tell because you're not voting. All right, here we go. Okay, we have a race. All right. Well, oh, here we go. More voters. All right. 2/3 say no, and the correct answer is no. Okay. But this introduces an important concept, which we'll run into again later on. What happens if we do try to take a square root of a negative number? Well, the square root of a negative number is said to be an imaginary number. And there's one in particular that you probably remember. The square root of -1 is often expressed with the letter I. Do you remember seeing that in high school? I, the imaginary number. So this is not part of the real number system. And in fact, we're going to see a video where they talk about this in more detail and explain it a little better. But within the real number system, you may not take the square root of a negative number. If you do, you're going to wind up with what's called an imaginary number, which is not part of the real number system. So we're not going to do a whole lot with that this semester, but it's important to know that these exist. They are very useful in certain disciplines like engineering, but we're not going to see it here very often. Now, that leads to my second poll question, which is, can you take the cube root of a negative number? And of course, the answer has got to be either yes or no. Okay, well, it looks like pretty much everybody's done voting. This time, the answer is yes. All right, so let's see how that would work. But before we do that, we have to remind ourselves, what exactly does it mean to take the cube root of a number? So we'll just remind ourselves that the cube root, let's say of 8, equals 2 because 2 times 2 times 2 equals 2 cubed is 8. Okay, so in other words, the cube root and the cube are essentially inverses of each other. All right, similarly, the cube root of 64 is 4 because 4 cubed is 64. So if I try to apply this to -8, I'll get -2 because if I multiply -2 by itself 3 times, I'll just get -8. So yes, you may take the cube root of a negative number. And we can generalize this even further. And by the way, in a case like this, you could just take it to your calculator. Your calculator should have, it may have a cube root number. If it does not, you can just raise that number to the, this can be written as a to the 1/3 power. Okay, so if you want to do this in your calculator, you take that number and raise it to the 1/3 power. All right. With a square root, there's no actual 2 here, but this is implicitly raising 8 to the 1/2 power. Now, there are higher roots as well. For example, we can have a 4th root. This equals 2 because 2 to the 4th is 16. Okay, so the way this works is as follows. Cube roots, let's do it like this. You can define any of them you want. These are said to be odd roots. And then these are said to be even roots for obvious reasons. So what am I doing this for? Because we can not take the even root of a negative number but we can take the odd root of a negative, wow, there's no space here, a negative number. Sorry about that. Okay, so in general, we cannot take the even root of a negative number, but we can take the odd root of a negative number. So in other words, I can have the cube root of -1, I can take the 5th root, the 7th, but not these even roots. Okay. And you can try, I mean, if you throw these into your calculator, you'll see right away. If you try to take the square root of -1, it'll just give you an error message. So with all that being said, the reason why I brought all of this good stuff up is because we're about to look at another function, which is, well, all right, well, you'll see. Are we ready? All right, we'll give everyone a minute to catch up with all this good fun stuff. Okay. A cube root function. All right. So now we're taking the cube root, and because we're allowed to take negative cube roots, all of a sudden, the domain is all the real numbers, which we write as the interval from negative to positive infinity. And it's kind of a weird looking function, as you can probably imagine. And by the way, Excel doesn't always do the greatest job with these graphs. That's where these are. So here we go. Yeah. So it's sort of like, it should be a little smoother than this. It's kind of jagged, as you can see, but maybe we could try this in Symbolab. But it's rising very quickly, but then it slows down after a certain point. So it slowly rises, and then it starts to accelerate very quickly, and then it just starts to slow down again. All right, yeah, I think let's try that. Let's go back to Symbolab for a second. I'm curious to see if what it looks like on here. Y equals 1 over x cubed. Oh, sorry, I did it wrong. It's x to the 1/3 power. Yeah, you can see it's not that different. It's just that it's very smooth here. That's the only real difference. But this is a proper graphing tool. The Excel is okay as far as it goes. But yeah, you can see it's nice and smooth. Whereas on mine, it's kind of, but there it is. Okay. Now, we've been talking a lot about domains and ranges, but in this section of the chapter, we're going to be given some formal steps to help us identify for any situation the domain of a function. Okay, so the logic here is that any real numbers that cause a function to become undefined are going to be left out of the domain, of course. In other words, when we had something like this, well, since we can't have division by 0, x equals 0 is not part of the domain. So imagine if we had something like this. What number would we have to leave out of the domain? What number would cause this to go to 0, division by 0?
2.
2, exactly. X equals 2 is not part of the domain. In other words, it's everything else. And you could write it as the interval from -infinity to 2, union 2 up to infinity, where remember, this curved parenthesis means that 2 is not included in either of these intervals. In other words, this means everything but 2. That's the way we write it. This is set notation because the real number line is actually an infinite set of numbers. Now, this can get a little tricky. Like, for example, here, you might recall this example from earlier. What if we had this? Oh, now you remember, this could be written like this. And that being the case, what numbers do not belong to the domain? Well, let's say x equals 4. What happens in the denominator? I get 0. What if x equals -3? I'll get a 0. So therefore, the domain is everything except these two numbers. And we can write it as -infinity up to -3, -3 to 4, and 4 to infinity. Oh, gets a little trickier, but remember, the whole point of it is to say that this is all real numbers except -3 and 4. But you might not have realized it right off the bat over here because you didn't, if you had not already broken this down into its two factors. So sometimes this can be a little challenging. It may not be immediately obvious if there's anything that's missing from the domain. Now, but on the other hand, what about something like this? What's the domain in this case? Remember, it looks like just like this. The domain is all real numbers. In other words, there's no value of x that could cause division by 0 or any other problem. So the domain would simply be everything from negative to positive infinity. Okay, it's understood these axes go all the way out to infinity, by the way. Okay, they do go on forever. So in other words, there's no value that's missing. So x would be, the domain of this function would be all the real numbers. On the other hand, the range would be all the positive numbers, because you can see y starts at 0 and then it goes up through all the positive values, but it is never negative. Okay. Are we looking? How's that looking? Are we getting it? All right. So now, what's coming next is a formal discussion about how to find a domain. Now, this is a fairly complicated topic, as you can probably guess. And you know what? Let's face it. Normally, what we would do here is have our second break, and then we wrap it up at around 11:30, 11:40. But because this is the first day back, there's no point in overdoing it. Why don't we stop right here and get out a little early today? I mean, let's face it, it's the first day of class, and the weather's kind of crappy out there. So I think we've earned an early dismissal today. But you know what this means? That you have to go back now and read through these slides and make sure you understand what we've done. And if you need to, the video will be available pretty soon, and you can go back and watch it. And then if you are still unsure about anything, you can bring questions with you next week. Now, this is going to take some getting used to, only meeting once a week. Every time I see you, it'll feel like a long time since we did this material. So what I will also do is go back and revisit the most important concepts we covered the week before we get started with the new content. Because again, after a week, it's possible that you've started to forget. We do not want that. We want to make sure everything's fresh in your memory and that you know what you're doing. And then in addition to all of that, what I would like you to do is take out these problem sets, at least the first two. Let me just double check this for a second. Okay, well, actually, we're really not exactly ready for number 2. So let's do this. Next week, we will just focus on chapter 1, practice problem 1, and because we haven't really gotten far enough to do number 2. So in addition to reviewing the materials and potentially watching the video, why don't you take a crack at these problems on practice problem number 1. We'll go over those next week and make sure we're all on the same page, and then we'll get back into the new material. So this is what we'll do every week. We'll review what we've been doing. We'll go over some problem sets, and then we'll start the new material. All right. And eventually we'll have a test. But before we get to that point, we'll have done tons of practice problems, and we'll also review for the test itself, just to make sure everything is fresh in your memory. All right. And in the meantime, you may want to take out your calculators and see if you can use them for some of these problems. Sometimes you'll be able to do it and sometimes you won't, depending on which one you have. All right. So are we all worn out? I could have a poll for that. Are we intellectually worn out today? Isn't it a good thing that this is your only class today? Yes, it is. Okay, so you can spend the rest of the day, I guess, doing other things that don't require such intense thinking. And I'll see you all next Wednesday. All right.
Thank you for your time, Professor.
Welcome.
Thank you.
Okay.
Bye. Thank you.
See you
All
next
right.
week.
Bye.
Have a good day.
Bye.
Okay. See you
Yeah,
later.
Professor.
All right.
Professor Anderson, I actually just had,
Yes.
how are you doing?
Okay.
I just want to know because I was in your stat class over the
I
winter.
remember. Did you
Yeah.
finish?
Yeah, I just wanted to tell you I'm almost done with everything.
Okay.
I wasn't sure. Did you want them like I could send you what I have so far?
I
Like
think that's a good idea. I would like to be able to work on them in
Okay,
stages rather than wait till the last minute.
okay, yeah,
I put in the what did I tell you? Was it the end of February? Right?
15th of February.
Yeah. Oh, 15th, whatever. They never told me yes or no, but as long as they didn't say that there was a problem, I assumed that was okay, because I realized that there is a spot in the website, their website, where you can ask for an extension, so I took care of all that by the due date. And so when you correct all this stuff, then I'll go back into the roster and I will fix your grade.
Okay, sounds good. Thank you so much. I have to like chapter 11 done. I think I just have to do midterm 2 and then the final.
All right.
And then,
Yeah, you know what? What you should probably do is just send them to me as soon as they're done.
okay, got it.
That way I can do them in stages rather than, having to take the whole batch and do it all at one time.
Got it. Sounds good. All right.
All right.
Thank
So I'm glad you came back for more.
you. Yeah. It's I'm an economics major, so that's why I have to.
Oh, there you go. The more math and stats you have, the better off you'll be. Definitely.
Yeah, of course. All right. Anyways, thank you so much.
All right. You're welcome. See you next time. Anyone else?
Professor, I have
Yes.
a question. Like, is there anything assignments?
No, just read the notes. No, you should work on this practice problem set number 1, but we're just going to work on it together in class. You don't need to hand anything in.
Okay, thank you so much.
All right,
And
you're welcome.
and I am an international student, so maybe I have some questions during
okay.
the semester. So
All right.
yeah,
Very good.
thank you so much.
All right. See you next time.
Yeah, bye.
Okay, bye. Anyone else? Okay, so I'll see you next time.